Good morning, good afternoon, and good evening, everyone. And a good afternoon to our audience at the ISAE conference in Helsinki. Welcome to attend our hybrid webinar today. And for those who don't know me, this is Yajun Pan, and I'm the Women-in-IES chair starting from this year. Today, I'm so glad to host our very first webinar for the Extraordinary Women-in-IES webinar series at the week of International Women in Engineering Day, which is on June 23rd. This webinar is co-hosted with IES Technical Webinar Series. Thank you, Cecile, for help on organizing this webinar with me. Today, it is honored to have our wonderful speaker, Dr. Lacra Pavel from the University of Toronto. She will give a talk on Nash's game theory of networks. First, I would like to introduce Dr. Pavel for a few minutes before her talk. Dr. Pavel is a professor in the System Control Group at the Department of Electrical and Computer Engineering at the University of Toronto. She received the Diploma of Engineer in Automatic Control from the Technical University Iași, Romania, and the PhD degree in Electrical Engineering from Queen's University, Canada. She joined the University of Toronto in 2002 after postdoctoral fellowship position at the National Research Council and 4 years of working in the communication industry. Her research interests are in game theory and distributed optimization in networks, with emphasis on dynamics, system theory, and control methods. She is the author of the book Game Theory for Control of Optical Networks. She is a senior editor for the IEEE Transaction on Control of Network Systems, a senior editor for the IEEE Open Journal of Control Systems, and an associate editor of our top control journal, IEEE Transaction on Automatic Control. Now let's welcome Dr. Pavel. Dr. Pavel, now you have the floor to present. Thank you.
Thank you, Ajun. I'm very happy to be here virtually. Thank you for your invitation. It's a wonderful occasion during this week of Women in Engineering. I'm going to present some of the results that have been developed in my research group over the past few years, I would say. And the topic is on extending Nash's game theory to networks. I have to first let me just see how do I move on to the next page. We didn't test this. I cannot test, so I'm going to exit. Nah, I cannot go to the next page, so I'm going to exit from the full screen mode. And let's see if this happens. Yeah, that's good. Okay, yeah. So I'm going to first of all acknowledge the work of my former PhD students, Diane, Bo, and Andrew, and Farzad, as well as my postdoc, Peng. I'm going to start with the fact that the motivation for this work is development and the prevalence of networks around us, in particular, engineering networks such as wireless networks or social networks. And in this sense, the idea of extending Nash's game theory to networks. But first of all, what's a game? So I'm going to start with a little bit of intro on game theory. The setup of a game is composed of a number of players, 2 or more, which are the decision makers, players, agents. Each of these players has a finite number of choices, or alternatively, a continuum of choices. And these choices are either called actions or decisions. At the end of the game, there's some payoff to be gained or some costs to be paid by each of these agents. And in standard optimization, there is a single decision maker who aims to optimize some goal, objective function. In a game, there are multiple such decision makers that are self-interested, and they have their own individual goals. So mathematically, we're going to denote the set of players by this set V made of n agents or n players, and I'm going to indicate each player with an index I. The action of each player is x sub I, selected from his action set, finite or not, or continuous. The player has an individual payoff, u sub I or cost function, and the goal is to maximize its own payoff or equivalently to minimize its own cost. However, his success in making decision, which means in minimizing his own cost or maximizing its payoff, depends on what the others are doing. Hence, the cost that you see here, J sub I, depends on the profile of all the decisions of all the other players. That X that you see there, it's an n tuple. It's composed of all of the actions of all of the agents. A compact notation usually isolates the decision of player I, X sub I, and the decision of everybody else. Everybody else except I has the action denoted as X minus I. So the game theory setup studies mathematically the strategic interaction among such multiple decision makers. What does it mean to solve? What does it mean for an equilibrium of such a problem? And how do we actually find such an equilibrium? A typical assumption that's made is that each of the players is rational. In other words, makes a choice that optimizes his expected payoff or minimizes his expected cost. Now, a strategy can be regarded as the rule for choosing an action, and there are different possible cases. One of the most common one is the security strategy, which is to minimize your own maximum expected cost, which would be the worst case scenario. And the resulting solution, where each player uses such a security strategy, is a minimax solution. Now, a famous game is a prisoner dilemma game, and this is a game between two criminals that have the choice of being the ones to confess or not to confess. And they're kept in two separate rooms, and they don't know what the other one is doing. Depending on their decision, they're going to get a cost that's represented by the number of years in prison. If both of them confess, for example, here, each of them gets 5 years in prison. If one confesses and the other one doesn't, one of them, the one that doesn't confess, gets scot-free, the other one gets all the blame. However, if neither of them confesses, they just get 1 year in prison. It turns out that the confess is the security strategy for either of the player, which means that the 5 years in prison is going to be the minimax solution for this game. Now, this is not the only possible solution. Alternatively to the security strategy is the so-called best response strategy, where the player would play the action that gives you the lowest cost, given whatever the opponents are doing. And this is represented by that inequality that you see here at the top of the page. A Nash equilibrium solution is when each player uses such a best response strategy. And this means that the inequality holds for all player I. Yeah. The equilibrium solution can be said to be at the intersection of all the best response strategy. The key of this equilibrium solution is that no player has any incentive to change unilaterally their action. In other words, they have no regrets. If the other ones are not changing theirs, player I doesn't have any incentive to change his. And this is the famous Nash equilibrium solution. As a result, Nash equilibrium is a relevant and an expected solution to be arrived at by a set of rational agents. Now, it turns out that that game that I mentioned, the prisoner dilemma game, that minimax solution is actually a no regret. It's actually a no Nash equilibrium. But there are other games that do not have a Nash equilibrium solution. Another famous one is the matching pennies game. This is a game that we've all been familiar with two people flipping pennies, and you see there in the matrix M the outcome where one loses, the other one gains. It turns out that this game does not have an equilibrium solution, but if we randomize their choices, and if each player chooses head with 50% probability and tail with 50% probability, the expected payoff is actually 0 for both of them, and this gives no regret for either of them. So this is an equilibrium solution in randomized or mixed strategies. And one of the famous results in game theory was developed by von Neumann almost 100 years ago, which says that for every two-player zero-sum game, there exists an equilibrium in mixed strategies, randomized strategies, not necessarily in the actions. This has been extended by Nash, even though we're saying that Nash is the most famous person in game theory. He actually just extended the result of von Neumann to n-player games, and he said he proved that every n player with finite action sets has at least an equilibrium mixed strategies. This was then extended to games with continuous action sets by 3 people simultaneously and independently, de Broglie, and Fan, which said that for such a game that has relatively mild assumption, the function ji being continuous, convex in xi, then we can have a pure Nash equilibrium. So these are basic, you see here, these are basic results in game theory more than 50 years ago, or 70 years ago or so. And the classical setting of game theory was relying on these 3 pillars. It originated and has been used initially in economics and social sciences, and it relies on the equilibrium analysis based on the Nash equilibrium solution or its refinements. What it does, it offers traditional explanation as to when and why a Nash equilibrium arises. It's assuming that the players have complete information about what the other ones are doing. They are very sophisticated. However, in the past 20-25 years, an alternative setting of game theory has been becoming prevalent, and that's of the learning game theory, where this setting is that a Nash equilibrium would occur in a repeated game where players would interact with each other for multiple rounds of the same game, and then a Nash equilibrium would arise as a limiting point of such repeated play. And moreover, less than maybe fully rational players are involved, and they might have complete information or not complete information. And in this setup, in terms of learning or updates of this player strategy, one could have various algorithms. And I'm listing here some of the most common ones: best response play, fictitious play, gradient play, reinforcement learning. There are quite a lot of them. Now, where is the network coming in? The network is coming in from the application scenario. So I put here a few of the scenarios where a multi-agent system or networks would entail the interaction between multiple entities with individual goals and the capacity to act. And that would be in transportation, congestion game, communication, routing games, economics. It would be the competition among various companies, social networks, the competition among users. And the major challenge is, do you do a centralized coordination among agents? Obviously, this is not feasible. So that's where the game theory network games come, in the sense of being able to develop algorithms and update rules for the players such that they arrive at a Nash equilibrium. And you see here listed several areas in which these results have been developed, as I mentioned, from congestion control in networks, be it internet or transportation, to power allocation in communication networks, mobile sensor network formation, resource allocation game in cloud computation, or demand response management in smart grids. The players can be either the network nodes, routers, channel, the robots, the network users. And they each have their own individual goal, and they might share the network resources in the sense of bandwidth, power, capacity. And over the years, there have been developed different results in different settings, finite action games or continuous kernel games, evolutionary games. So what I'm going to talk about is going to be mostly in the, not mostly, it's actually in the continuous kernel game setup. And I'm going to try to address these challenges: complexity of the network interaction of the agents, the fact that they might have local or partial information and not complete information, and as well the fact that they might have delayed or asynchronous communication. So I'm going to start with the setting, and I'm going to have that agent I having its own individual cost JI or payoff UI. But now I'm going to assume that JI can be affected by the subset of the other players. Those could be all of them, but not necessarily all of them. And this is modeled by an interference graph or conflict graph. That's the J sub I that you have there at the top. And then I'm going to also assume that the information is going to be obtained over a network that's going to be described by a communication graph. That's G sub C. And these two graphs can be identical or not, complete or sparsely connected, directed or undirected, static or time varying. And this is the setting of game theory over networks. The problem is then to start with such a setting and to be able to characterize the game, the solution, and to develop the algorithm for arriving at a Nash equilibrium. And you have here listed different cases for this interference graph, for example, from complete to partial, undirected to directed. And then the communication graph, it's going to be either identical, which means that they're going to actually have complete information, or a subset. And this is actually the partial information that's the most difficult one. Some of the assumptions that I'm going to make is that this communication graph over which communication happens is connected and undirected. And I'm going to make some basic assumptions that ensure the existence of a Nash equilibrium. Standard ones. The action set of each of the players is non-empty, compact, and convex. And then the cost function is continuously differentiable. This is what C1 means. Convex in X sub I, which means convex in their own action, and jointly continuous. And then I'm going to make some assumptions on the stack of partial gradients. So this is going to be a key instrument in what we're doing. This is called the pseudo gradient. And in the case in which all of the cost functions are identical, this is actually a true gradient. But in general, in a game, this is not a true gradient, and that's why the name pseudo gradient. The assumptions are going to be that this pseudo gradient, capital F, is either strictly monotone or strongly monotone. You have there the two inequalities that characterizes. I'm just going to make the connection that in the case in which this is a true gradient, strictly monotone amounts to saying that the cost function is strictly convex. Strongly monotone amounts to saying that the cost function is strongly convex. But again, this is the more general case. We don't have a true gradient. We have the monotonicity just in terms of this pseudo gradient. And the objective is to design a distributed algorithm to find the Nash equilibria of this game using only partial information over the communication graph GC. To do that, I'm going to start by, first of all, setting up the case for developing an algorithm first in the perfect information case, and then I'm going to tell you how we can extend it to partial information. We'll start from the characterization of a Nash equilibria. And remember that we said that a Nash equilibria lies at the intersection of all the best response mappings. This is comes all the way from Nash, and this is what you see over there at the bottom of the page. Once we introduce the continuously differentiable cost function, this NE can be characterized in terms of an inequality that involves the pseudo gradient f, and you have that inequality Vi over there. That characterization can be expressed in terms of the fixed point solution that you have there in the FP equality. And this is telling you what? It's telling you the fact that a Nash equilibria, which is made of the n tuple containing all the optimal solution of each of the players, can be obtained by each of them. You see x sub I star solving for this equality, and this happens for every I. And what you see there, and you have actually what? This is an implicit equation. On the right-hand side, you have a projection on the action set, and then the argument is again x sub I star minus the partial gradient of its own cost. That depends on the other's decision, x minus I star. So this in first instance, it's showing you that in order to arrive at this Nash equilibria, the agents must know its own cost and all the other actions x minus I, which is what we call the perfect decision information. So first of all, how do we get to a solution of this equation, set of equations, in an iterative manner? And this is what we're going to go next. We're going to assume perfect information, which amounts to saying that the graph G sub C is complete. You have the depiction there for a small number of players. And the idea is to use a fixed point iteration, which means to assume that at each iteration, each player is going to update its own action. You see the xi at k plus 1 based on the previous iteration right-hand side. So everything that's on the right-hand side, it's at iteration k. Yeah, except that I see here, and you see here that it depends on the other one's action, x minus ik, that's in red. In stack form, this is expressed in terms of the pseudo gradient as in 2. And this algorithm converges on the strict or strong monotonicity of the pseudo gradient f with either diminishing or constant step sizes. Again, a standard result. Now we're going to actually look at the case in which I have an alternative. Instead of discrete time, I'm going to assume that I have very small interval between the updates, and I'm going to approximate this in continuous time by a differential inclusion, and then I'm obtaining actually a set of differential equations that's 3. And this is the continuous time variant of this projected gradient algorithm. And you have the block diagram there that's showing you that this algorithm 3, it's represented by this feedback interconnection between all of the players. Here, remember that X is the n tuple of all of the decisions. Good. So now we go to the partial information case where the graph GC is no longer complete, and you have there in the figure in the top right corner. We're going to assume that each player knows its own cost function and action set, but does not know the other one's actions for all of them. He can only see and communicate with his own neighbors in the graph of communication GC. And the idea is that based on this communication with the neighbors, he's going to build an estimate of what all of the others are doing. And I'm going to call that estimate bold x minus I with superscript I. And the idea is that ideally by communicating with their own neighbors and assuming that the graph is connected, they should arrive at a consensus, which means that they should arrive at a common estimate of all of the others. And this is inspired from the typical consensus problem, where you have a set of n agents, each with a different variable. Now this variable is sub xi, and they communicate locally over a partial graph. And they actually compare the relative difference versus their neighbors. This is what you see there in the top, the difference. And it turns out that this is expressed in terms of the Laplacian. And if iteratively this is done over this graph, then they eventually converge to a case in which you have all of them arriving at the same value. So you see here illustrated in the bottom figure here by all of them arriving at the same color of the xi's. Now, in the case of a game, they each have their own action, but that action is part of the n tuple. So it's a little bit more complicated in the sense that the consensus is on a vector. So they should arrive at the same n tuple, and this is what you see here at the right, far right. You have n tuples, but they have the same structure of the coloring. So that's the idea. Combine consensus of the estimates with a basic projected gradient so that the agents reach both consensus and converge to the Nash equilibria of the game. And this is what my PhD student, Fred, developed in his PhD thesis and then published in Automatica based on a gossiping step where two players are selected at random and they communicate and then they exchange, they average their estimates. And then at the local step, they do the projected gradient where you see instead of the actual actions of all the others, they use the estimate, which is that green, bolded green value. And we were able to show that under, again, the same type of assumption, strict monotone and Lipschitz pseudogradient with diminishing step sizes, all of these estimates converge to the consensus and the players converge to the Nash equilibria almost surely. Moreover, we have treated all of the possible cases for the interference graph, complete or sparse, directed or undirected. And this can be done by appropriately modifying step one. All is nice, except that this convergence with diminishing step sizes is very slow. It corresponds to a 2-time scale continuous time projected gradient with a fast and a slow subsystem. While if you use constant step sizes, you can only converge to a neighborhood of the Nash equilibrium. You do not converge exactly. The idea then is to use some other correction term to overcome this. You can either do this in the continuous time with correction or in a constant step size with correction via an ADMM approach. And this is what I'm going to tell you a little bit about. So the first one is the correction via the projected gradient dynamics, continuous time. The same setting, but now I'm going to look at actually designing a new continuous time single time scale. In other words, not that slow diminishing step size like. And what I'm going to exploit is that monotonicity, which amounts to passivity in dynamic systems. And this is where another of my PhD students, Dian, proposed this correspondingly projected gradient dynamics, where you see here at the top, this is the equivalent of what you see before. On the right-hand side is the projected part and the partial gradient, but there's the extra term. And that extra term is the involving the comparison to the neighbor's estimates, and that's the correction. And then the second line is just purely the update of the estimates based on the neighbor's difference. Compactly writing this in terms of pseudo gradient, which is actually in terms of the estimates, meaning that I have now an extended pseudo gradient, bold F, because I'm using only the estimates. and making an assumption that this extended pseudogradient is Lipschitz continuous, one can show that in a block diagram, I have a similar algorithm that I have an extra feedback loop that through the Laplacian. And this extra feedback loop can be then exploited together with passivity to show that if the communication graph is sufficiently connected, then the solution of that algorithm will converge to the Nash equilibria, and all of the agents will converge to the same consensus. And again, this was by introducing that correction in continuous time. Now, discrete time, because usually we implement algorithms in discrete time. We've used here with Fred the idea of ADMM, which is to actually introduce an embedded consensus constraint plus some regularization, and then using for each of them an alternating dual multipliers method approach. And the algorithm then is going to be represented as you have here. I'm going to start with number 2, because number 2 is exactly the projected gradient method plus a correction term. And that correction term, you see again that you have something similar that involves the estimates from your neighbors, together with an extra variable W that's updated in 1. Again, you see the difference between the neighbors' estimates. And then the last one is just for the estimates doing averaging. So in this case, again, we were able to show that for sufficient choices of step sizes that are constant, no diminishing, and that are related to both the game and to the connectivity of the communication graph GC, then the sequence generated by this algorithm converges to the Nash equilibrium. This is quite a strong result, and it overcomes that weakness of the just purely projected gradient dynamics with estimates that was using diminishing step sizes. So now I'm going to present you some examples. So the first one is on an economic game example among n firms that are producing a homogeneous commodity, and each one is trying to maximize their own profit. And obviously the total quantity produced determines the demand price, and what the other ones are doing influence the profit that you get. So this game that we've considered is between 20 players. The cost function for each player is the JI, and it has a quadratic form that involves both the production cost and the demand price. And we're going to assume that the players are scattered around the globe, you see here across the continents, and that I'm going to run the continuous time projected algorithm for different communication graphs. Again, communication graphs here, in this case, you can think of them as being spread out across the globe. The first case is when I have a random communication graph as the one depicted on the right here. And on the left, it shows the actions, the dynamics of all those 20 players as they reach the Nash equilibria. And you see that it takes about 300 time steps there. On the other hand, if the communication graph is very sparse, and this is a cycle communication graph, the one that you see here on the right, this is the absolute minimum that one could have. One can see that actually this convergence is much slower. Yeah, so if I go back here, I can say, well, convergence is actually up to, let's say, 150. Yeah. Here I go to 300 and they still have not reached the Nash equilibria. So this is showing you the importance of what I was saying, that if the communication graph is sufficiently strong, and depending on how strong that is, the settling time can be different. The second example is going to be from a wide area wireless network rate control game. So I'm going to assume that we have an ad hoc network composed of 15 users, and each of them decides the rate with which they're going to communicate through a certain path through the network that they have to transmit, and that these mobile nodes are connected by 16 links that each has a maximal capacity. And this maximal capacity is encoded by this affine constraint that you see there. The sum of all of the rates has to be below the capacity of each link. I'm going to assume that the cost function of the player has an utility component. You see there the log function that depends on the rate with the minus, which means that the higher the utility, the lower the cost. And this is directly proportional on the rate. And then we're going to introduce a price component that's going to penalize player if they get too close to the capacity. And you see there the inverse proportionality term there. And I'm going to assume that we have a communication graph as the one depicted here at the bottom among these 15 players. And I'm going to show you the simulation results for 3 algorithms. The first one is, the red one, is the projected gradient with diminishing step sizes. That's the first one that I presented to you. The black one is the same one with constant step size, the one, and the last one, the light blue, is the ADMM one. And let me just see if I run it. You see here at the far right, you have the Nash equilibria with a star. That's where they're supposed to arrive. And then you have here the iteration and the data flow for the 8th user. And as you can see, the projected gradient with diminishing step size is the one that goes very, very, very slow. The ADMM, it's quite fast, and it seems to be already on track. It's already at the level that's supposed to be. And in black, you see the PGA, the projected gradient with constant step size. You see there that it's converging. It's converged. Now it's oscillating around, but it's quite an offset from the actual Nash equilibria. And if you let it run up until 1,000 iterations, you're going to see that it's still not able to overcome that offset. And this is to show you that, in essence, that correction term that I was mentioning is actually essential in order to overcome the slowness of the convergence with diminishing step sizes. Yeah. Good. Finally, I'm going to conclude with a social network example. So I'm going to consider just 5 users, either your Facebook or your Instagram, you name it, you pick your favorite social media. And each of them produces exabyte unit of information that the followers can see in their news feeds. And I'm going to assume a strongly connected communication graph, G sub C, where I'm going to say that I is connected to J if J is a follower of I. In other words, J receives the unit of information produced by agent I in his news feeds. I'm also going to assume a strongly connected interference graph, J sub I, where I'm going to say that I is connected to J if J is influenced by I. In other words, J is following I. Yeah. The idea is that this J sub I includes the attention drawn from the network also. Yeah, and you see here at the bottom the 2 graphs, and you can see that the communication graph is sparser than the interference graph. And here we're going to consider that the cost function of each player consists of 3 parts. The first one is the posting cost. That obviously is linearly dependent on the amount of units of information produced, and then a payoff from the users whom I follows, and this takes the form of this FI1, and then also the attention from the network. So this is a form that other researchers have proposed, and we've tested this for the algorithm that Fred developed. And here you have the results. And what this result is telling you is that the Nash equilibria that is arrived at indicates that, in fact, players 3 and 4 have more followers, more attention. They tend to produce more information. Quite common sense. On the other hand, also player 5 receives information from 3 and 4, and then this is going to be also greater than what 1 and 2, because as you can see here, 1 and 2 do not have that. So with this, I'm going to summarize that I've talk to you about some of the recent work that we've done on distributed Nash equilibria in extending the theory to networks. And this was for a Nash equilibria concept solution. And there is a lot of other areas that people have been working on, and there are open questions. Some of these are, how do you extend to games that actually have constraints that are coupling the actions of the users? This is what's called generalized Nash equilibria. How do you reduce the processing or the memory requirement? Remember that each of the players here, it is assumed to build an estimate of what everybody else is doing. If you have a game or a network with 100 users, each of them is going to have to maintain an estimate of a vector of 100 elements, which is quite large. Can we relax those? Can we relax some of the assumptions that we have, technical assumptions, that strong or strict monotonicity? Also, a key point that was actually here assumed is the fact that when they're exchanging estimates, they are truthful. How do we deal with the case that you could have cheating players? Finally, what about extending and relaxing even more? No assumption on the own cost, but only realized in game payoff, which means reinforcement learning. And this is an area that is quite recent and quite active right now. So with this, I'd like to close here, and I'm happy to answer any questions you might have. Thank you.